So this is example number one for source potential. In this particular example, let's consider a simple combination of a source and a uniform flow. Now, the secret word is a combination. So you have the source and you have the uniform flow. So by this information, you already know that your total potential would be the potential of the source plus the potential of the flow. It's the combination of both. The free stream velocity of 100 miles per hour. The question is, what strength must the source have to place a stagnation point at 2 feet in front of the source center? And for sea level conditions, find the velocity and stagnation pressure in the flow at x equal to 4 and y equal to 8. So basically, this is the source field that we are talking about. We're going to assume this is completely uniform. And RS is distance from here to here. So the question is, what has to be the source? What has to be the value of this Q right here? What should be this Q such that this RS is actually equal to 2 feet? Okay, and we are working with sea level conditions. So for sea level conditions, this is 0.00237 slug speed squared cubed. 100 miles per hour is the same as multiplied by 88 divided by 60, and that gives you 146.7 feet per second. RS is equal to 2 feet. Again, is from here. We want to find the Q, V, and P. Okay, so let's start the problem. First of all, because let's see the potential velocity. What will be the total potential velocity? So because of continuity or conservation of mass, this is equal to 0. So we know that your source has to equal to 0. We also know just for the flow itself has to be 0. But since this is all 0, I can add them up. So therefore, this gives you the Laplace of the source plus the potential of the flow. Okay, all of this is equal to 0. So therefore, we know that this is actually equal to the source plus equal to the flow. Okay, so in other words, the total I will be, the source is minus Q 4 pi r. We derived this in class. Plus U infinite r cosine of theta. Okay, so this information is actually known to us. The second thing we're going to need in the problem is we're going to need to know what our we need to find this point here, such there's a stagnation point. So we need to know our velocities. Okay, number 2, velocity components. So the velocity component of UR is equal to partial of phi respect to R. And that gives you U infinite cosine of theta plus Q 4 times pi R squared. U of theta is equal to 1 over R. Partial of phi respect to theta is going to equal to minus U infinite sine of theta, right? We also did that in class. So on the x-axis, okay, so on the x-axis, we know that theta will be pi and it's going to be 0, right? when I put 0, you can see that uh, u of theta is automatically equal to 0, okay, at both in these locations. Now at and then at pi, because I'm interested in this location right here, theta equal to pi, you can see that your UR becomes following: U infinite cosine of pi plus Q 4 pi r squared. And at stagnate, so this has to be 0 because we want to find the Q as stagnation point. Okay, so now we go ahead. If that's the case, this gives you -1. So in other words, what you find is that your Q of pi r squared is equal to V infinite. And from here, you find that your Q is equal to 4 pi r squared V infinite. Okay. Now, at stagnation, the value of your R is the value of RS, 2 feet. And you can see that, right? Because I want to know what is the value, the stagnation point here is here, and that's located at a distance RS, and RS is actually equal to 2. So I know that this point right here that I'm evaluating is at distance R. This is total radius. Okay, so if that's the case, then your Q becomes 4 pi RS squared V infinite. So if I replace the values now, your source then becomes 4 pi 146.7 feet second times velocity times RS squared. This is 2 feet squared. You evaluate this whole thing and you find that Q is equal to 372 feet cubed second. Okay, so this is your volumetric flow, the total volumetric flow in your problem. This is the amount of the strength of your source. Okay, this is the strength of your source such that this will be located at this distance. Okay, now let's see, what's the second question? Second question is find the velocity and the stagnation point at sea level. Okay, so now we need to go ahead and find the velocities. The velocity is given by the following. These are my velocity components. And the location I want to evaluate here is, I want to evaluate all of this at x equal to 4 and y equal to 8. We also know this is equal to r cosine of theta. This is equal to r sine of theta. Okay, so if I want to find my r, I can basically say, you can show that your r is nothing else than the x squared plus y squared. That would give you a value of 16 plus 64. So your value of r is equal to 80. Okay, so at x equal to 4 and y equal to 8, this is your radius. Okay, so this is the value for this radius. And so if you want to know what the value of your cosine of theta is now, if you need this angle, cosine of theta will be from here 4 over r, and that would give you 4 over square root of 80, and sine of theta would be 8 over r, that would give you 8 square root of 80. Okay, so let's plug the numbers in here and let's see what we get. So now I'm going to have UR is equal to, okay, so we know this is 146.7, and cosine would be 4 over square root of 80 plus your source. We found the value for source 7372 divided by 4 pi square root of r. Remember, this is going to be your r is equal to square root of 80. So this would be 80. Okay. And then this value will be minus 146.7. Sine is 8 over square root of 80. You can see we found the value here. So you evaluate this, and this gives you 1040. I'm sorry. This gives you 73 feet per second, 72.9. And this gives you minus 131.2 feet per second. Okay, so my total velocity then is nothing else than UR squared plus U theta squared. Remember, this is at x equal to 4, y equal to 8. That's the point we are evaluating. Okay. So this will give you a value of minus 131.2 squared plus 72.9 squared, and your velocity is at that particular location is 120.12 feet per second. Okay, so we found the velocity. So the next thing we want to find is stagnation pressure. The stagnation pressure is defined by P sub 0 is defined by P infinite plus 1/2 rho infinite V infinite. Remember we derived this in your notes. You should have this equation. Okay, so this would be 14. I need to multiply by 144 to get in the right units, plus 1/2, 0.00237, and then the velocity is stream velocity 146.7 squared. That would be 1 minus the velocity we found here, 150. So 150.2 divided by 146.7. All this is squared. So if you evaluate the whole thing, you will see that the value you get is 216 feet pounds squared. In other words, your stagnation pressure is 14.66 psi. Okay. So this is how we solve these problems. Now that we are here, let's go ahead and see what if we were asked to find the drag, right? What would be the total drag on this particular, over this particular, the surface of this body? So we're going to do the following. In our class, we derived the following equation. So in class, we derived the following equation. One minus 4 times R over RL squared plus 3 times R over RL squared. Okay, we derived that in class. So we know that the drag equation also derived in class was actually equal to R sub 0 to RL PR RdR. So we're going to plug all this expression inside here and let's see what happens. So the whole equation then becomes so this the first term is 0 because it starts at 0 to RL. Then is P infinite R dr plus the second term. This is 2 pi 0 to RL 1/2 rho V infinite squared. Then you go to the second term minus 2 pi 0 to RL of 4 times RL squared. There's a RdR. There's a RdR minus RdR. Then they have next term. This is all multiplied by 1/2 rho V squared RdR. And the last term is 2 pi 0 to L 3 RdL squared 1/2 rho V squared RdR. Going to save some math. This is integration, quite straightforward in all this. The R's basically remain constant. So if I integrate this, you can show that the answer you get is pi RL squared P infinite plus pi rho U infinite RL squared divided by 4 minus pi rho V infinite RL squared divided by 2 plus rho V infinite RL squared divided by 2, divided by 4. So if you look carefully, got a 4 there, you got a 4 there, and so you can just show this whole thing is actually equal to 0. So your drag then is basically equal to P infinite pi P infinite RL squared. And if you remember from your notes, where we said that RL is nothing else than 2 times RS. So then your drag is actually equal to uh, 4 times pi P infinite RS squared. These equations, the two equations are quite general. They're not bound by this particular problem. If it's a semi-infinite body, then this equation will always apply. Okay, so we also know that your RS is given in the problem. But if it was not given in the problem, regardless, this was equal to Q 4 pi u infinite, right? So then you can show that this is equal to, replace that in there, and this nice equation shows up here, which is quite handy to be used. Okay, for semi-infinite body, this is what you have. So let's replace the values than what we had in our problem. So this is equal to 4 times pi 14.7 multiplied by 144. Remember, change the units. Um, to squared, and that gives you 106,402 pound forces. That's the total drag acting on this body. So this will conclude this example. So you can see that you don't have to always sit down and rederive all the equations, just use what was derived already and just move on with that.